All right, this video can be used kind of supplementary to what we've already covered in class. So we kind of already went over this material on page 6 of the chapter 19 notes. And what we said there is that this chapter is about carboxylic acids, but it really moves forward to physical properties and how to separate things using extraction techniques. And extraction techniques, as we talked about on page 6, separate things based on their charge state. And one of the bullet points says, generally, ions are soluble in aqueous solution, so water, whereas neutral species are soluble in organic solvents. So if we had a mixture of this carboxylic acid and this alcohol, as the neutral species, both of them are soluble in organic solvents. So if we took this mixture and the first thing we did was, and let's kind of take a step back. What might we have? We might have a solid from somewhere that has a mixture of two different components in it. And we are trying to separate those two components to understand what is in that mixture. So the first thing we would do is just put them in a solvent that both of them are soluble in. So that's step one, dissolve both of them in DCM. But they may have different solubilities if we can make them charged. So the next thing that we're going to do is add an aqueous solution of sodium bicarbonate to that organic layer. So what is the bicarbonate going to do? Well, bicarbonate is a base, so this is showing the bicarbonate with the carboxylic acid here. And what do bases do? They take their electrons and they deprotonate acids. So what do we have here? We have a carboxylic acid. So on this side of the equilibrium arrows, we have the acid, and the base deprotonated that acid to form this conjugate acid on the other side. And what we've talked about before is that the equilibrium moves away from the stronger acid, so we need to know what the pKa values are of these different acids. Carboxylic acids are generally about 5, and this carbonic acid is 6.4. So as far as the equilibrium of this, the carboxylic acid is the stronger acid, so the equilibrium is going to be on this side. So that tells us that when we treat this mixture with sodium bicarbonate, this is going to be the form of the carboxylic acid. It's going to be anionic. What about our alcohol over here? The alcohol has a pKa of about 16. Still, the carbonic acid is going to have the same pKa it had here. They always have the same pKas. So in this case, the carbonic acid is the stronger acid, which tells us that this equilibrium is going to be over here. So we had this mixture of two organic soluble compounds, and by treating them with a base, we selectively deprotonated this species here. So we can say this is the aqueous, and in the aqueous we're going to have the carboxylate, so the anionic form, and in the organic layer we are going to have the neutral compound, so that would be our cyclohexanol. So we've already separated them. If we wanted to get the pure compound to characterize spectroscopy, to characterize using spectroscopy like NMR and IR, etc., what we would have to do now is remove all the dichloromethane. That's really easy to do. Dichloromethane boils at like 38, I think, maybe 40 degrees Celsius, so really low. But this is in water, and it's also mixed with a lot of this bicarbonate anion. So if we going back to the cyclohexanol, if we want to get that to look at spectroscopically, all we have to do is remove the dichloromethane, and we can use that with the Rotavap, the rotary evaporator, the ones we've used in lab. We could also just wait for the DCM to evaporate. It's going to happen pretty quickly because it has a low boiling point. Water has a higher boiling point, so it's going to take longer to evaporate, one, and then two, The other thing complicating things is that there's going to be a lot of other sodium bicarbonate left over in that water. So even if we got rid of all the water, we're going to have this mixed with a bunch of sodium bicarbonate. So what we're going to do to separate this from the water and get it back into an organic layer is we're going to treat this with, we're going to add, so this is just this in water. We're going to add, we'll add more dichloromethane, and then 2, we're going to add HCl to that solution. So we're going to add aqueous HCl. So what is that going to do? Well, if we have our, so this was the equilibrium in the first step, but now we've added an acid to our carboxylate. So our carboxylate looks like this, and we've added HCl to that. The pKa of HCl is about -7. So if this carboxylate takes that proton, it would form the carboxylic acid, and Cl minus. The carboxylic acid's pKa is 5. So again, we've added a stronger acid. We've forced the equilibrium over to here. So at this point, we are going to, once we add the dichloromethane and add more HCl, we're going to reprotonate our carboxylic acid, and that will make it soluble in the dichloromethane. So that's what we need. We need our analytes, the things that we're trying to analyze, to be in organic solvents so that we can remove those organic solvents and characterize them spectroscopically. So this was the procedure to remove a carboxylic acid from an alcohol. You guys are going to figure out how to potentially even remove more components. So that'll be coming up. So let me know if there are any questions, and hopefully this was a helpful review.